Okay, guys. Assalamualaikum and very good day. Okay, so today I'll do a little bit of recap on what we have learned. So this recap is like a revision. I hope that this recap will help you in answering the test, which will be done tomorrow, and also for your final exam. So in this lecture, I will emphasize which part is important for you to master it or for you to understand and know how to do it. Right, so okay, just go through this slide. I will give you the link for this slide and you can download it and refer to it later. Okay, class. So we start with the introduction first. So the basic concept of microprocessors, because 8085 chip that we are studying this semester is fall into one of these microprocessor category. So there are a lot of other name. We where we have heard in this computer world, where we have heard microcomputer and also microcontroller too. So what's the difference between these three? Is that microcomputer is a computer with a microprocessor as its CPU, and it includes the memory, I/O, and etc. That means microcomputer is like a complete build of a computer where it has a separate microprocessor which act as its CPU, and they already connect it to the memory and also I/O. That is what we call microcomputer. Microprocessor is just one single silicon chip which includes the ALU register circuits and also the control circuits. So only one chip that has ALU register and also control circuits, that is what we call microprocessor. And then the microcontroller is a silicon chip which includes microprocessor, memory, and I/O already included inside one IC or one integrated circuit. That is what we call microcontroller. Okay, alright, let's go to the next page. Okay, whichever I skip, you can go through it, but I just want to show whichever the slide that I think that it is important. To be frank, class, I haven't seen the your test exam question and also your final exam question, but I'll try to emphasize whichever I think is important for you to understand it. All right. So what else? Okay, this is okay, and then these are the basic microprocessor based system. So when we say a system, it should be completed with other things. So in the middle here, you can see there's a microprocessor, and there will be input devices that being connected to the microprocessor, and also there will be output devices that are also connected to the microprocessor and also memory. Here, these are the basic important components which complete the microprocessor system. And then inside the microprocessor, there will be three main units, which is must have thing inside the microprocessor. That is your ALU. ALU stands for arithmetic logic unit, which will do all the calculation and the arithmetic operation. And then there will be also control unit, which will control all the control signals that will control the input and output and also the memory devices. And then inside the microprocessor also they have an array of registers which is used to hold the data while it is being manipulated. So every processing which use the data will be stored in the register during the processing. And this is the more details what is inside the your microprocessor here, and this is your microprocessor base system. When we say system, it being completed by the I/O and also the memory, and all of this I/O and memory is being connected to the processor through system bus. Okay, and then yeah, this is the uh, memory that we have inside the system. The first one is the register itself, which is resided inside the microprocessor, and also there will be a read-only memory room, sorry, read-only memory, which is room that where we use to store information that does not change. Normally, this is your program code, your instructions code will be stored inside the read-only memory, and then this is random access memory, which will use you will store whatever data throughout the processing. I mean, like yeah, throughout the processing. So this is random access memory, which is it is volatile. All of the data will be gone if you take off the power. Okay, this is the memory map and addresses. I mean, which I've already covered in the previous lecture where I talk about memory. So as you can see here, I mean, this is just the diagram here is just to give us the understanding how we can connect various devices, memory devices to the processor. For example, here EEPROM here. EEPROM is the ROM type of ROM memory, read-only memory. So if you want to connect to, I mean, this is different device. This is one single chip EEPROM. If you want to connect EEPROM, you can assign the address of EEPROM from 000 to 3FFF. So all if any address that falls in between this address range will refer to EEPROM, and you can also connect to one RAM chip where you can use this address range to refer to RAM 1. If you want to add another RAM here, you can use the another address range 6000 up until 8FFF. So this diagram is just to give you the basic understanding how you can do the addressing of uh, various memory devices. Okay, and then this is three cycle instruction execution model which being used inside the microprocessor. I mean, the three basic execution model. The first one is fetch. So the first thing that microprocessor will do is that it will fetch the instruction. So I mean that is the fetch cycle where it will fetch the instruction and bring it back to the processor and store it inside the instruction register, and then it will decode it. Yeah, after it decode it, I mean then the processor know what to do based on the opcode that it fetch, and then it will decode it, and then based on the decoding now it can execute. So these are the three basic cycles in the instruction execution model. So I mean fetch, decode, and also execute. Okay, so I mean different type of microprocessor have a different number of data bit. For an example, the 8085A processor that we use, microprocessor that we use, which is Intel microprocessor chip, mean they use 8 bit of data line, which means that they can have 2 to the power of 8, which is 256 of different combinations of instructions or opcodes. I mean, this is the maximum, but then from Intel, they just use 246 bit patterns, which they form 246 different opcodes for the to operate the 8085 microprocessor. Okay, what else is important? Okay, now 8085 microprocessor architecture. All right, this is the basic information about 8085 microprocessor. The first one, it is 8-bit microprocessor, because normally if you talk about microprocessor, people will ask you, mean how many bit is your microprocessor. So normally you have to know this. For example, 8085 microprocessor is 8-bit processor, and it capable of addressing 64K of memory. Means here 64 kilobytes of memory. Different processor, again, they have different capability of addressing the memory. So for 8085 it can address up until 64 kilobytes of memory, and it has 40 pins here. I mean, we can see here they have 40 pins, and also it requires 5-volt power supply. So to operate this chip, you have to supply the chip with 5-volt power supply, and then it can operate with 3 megahertz clock. This is the clocking, where you have to provide the clock so that the processor can operate. I've talked about it, I mean, in my previous lecture, I mean, how the clocking is important because it will define how fast is your processor can do the processing. So for example here, I mean, for 8085 it can be operated by using 3 megahertz clock, and 8085 is upward compatible, which means that, I mean, it is compatible with the other various family of the microprocessor from Intel. All right, this is the how it looks like on the package, on the chip. As you can see here, there are 40 pins, and each pin has different function. For example here, X1, the pin 1 and P2 is being used to connect it to the frequency generator, where you connect it to either X1 or X2 to supply the frequency generator. And then what else here, you can see here, this is a multiplex address bus, where, I mean, this is address, it can be address bus, and also it can be the data bus here, the AD, remember, AD7 up until AD0 up until AD7. And your pin 40 is your power supply, and pin 34 is your IO, input output or memory read signal. So these are all the output pins that you can connect it to the other devices outside of the microprocessor, for example your IO devices or your memory devices. Okay, this is the simplification of the how the package look like. So these are all the interrupt signal. I mean, this is an input signal to the microprocessor, so you can connect whatever switch or whatever method where you can activate the interrupt signal to send the interrupt signal to the microprocessor. And here is the frequency generator, and here is your supply, and this is a high order of address bus, A8 up until A15. And then here is the low order of the address bus, or we call it as a multiplex address data bus. It can be address bus and it also can be the data bus. And here are the control and status signals, ELE, IOM, S0, S1. These are all the control and status signal. Yeah, here's your clock out and the reset out button. Sorry, output pins. Okay, okay. As you have to know that for the 8085 microprocessor, we have three main bus. The first one is your address bus. Address bus is unidirectional. Unidirectional means that it can only move one direction. So for your address bus, it can just move outward. So here is, as you can see here, this is the address bus, right? So the arrow is just pointing outward. That means the signals come from the microprocessor and being sent out to the your memory devices. So it's just one direction, and the purpose of the address bus is to identify peripheral, means that to identify which memory devices that you want to talk to, and also it also specify the memory location, which specific memory that the microprocessor is referring to. And then the second one is the data bus. The data bus is bidirectional. Okay, why the data bus is directional? Because this data bus can be used for the microprocessor to send the data out for example, to the memory to store the data. And also this data bus can also be used for the memory to send the data to the microprocessor. So that's why the data bus is bidirectional. And also the purpose of the data bus is to transfer the data. For here is, if you remember, this is multiplex, means that it can has two function here, the bus. It can be the address bus and also it can be the data bus. If the ALE signal is high, then that means this bus is being used as the address bus. If the ALE is low, that means the bus is used as the data bus. This is all you have to remember. You have to memorize it, class, so that it's easy for you when you're answering the test or the exam. All right, and then the last one is the control bus. So the purpose of control bus is the synchronization signals. For an example, you want to read to the IO. So here, I mean, you send the signal high. When the signal from pin 34 here is high, that means you want to read from the IO. If the signal is low, that means you want to read from the memory. That is what we say control signal. And then the other good example here, read and write. If the signal here is low, from pin 32, the RD signal, if the output signal here is low, that means we want to read from the memory. So we are reading from the we connect this signal to the memory, and we are, if the memory receive the signal from pin 32 here, and the signal is low, then the memory knows that the microprocessor want to read the data from the memory, so it will allow the microprocessor to read from the memory. If the write signal is low, that means the memory will know that the microprocessor want to write the data to the memory. This is how it communicate with the microprocessor. Apart from by using the address, it need to be assisted by these control signals. It can also be used as the timing signals, so that they know when the processor is done with the reading or writing. And then also the control signal. Okay, this is more details on what is inside the microprocessor. For example, here, class, as you can see, there's an accumulator, and we have temporary register here, and we have flag flip-flops, and we have instruction register, and these are all the set of registers that we know. And we have stack pointer here. We will review what is stack pointer all about, and this is a program counter. And we have the all of the registers being connected to the ALU, and all of these have been connected to 8-bit internal bus. They have internal bus for that the data can move around from one register to the other register. And also here is the address buffer, where it can buffer the address, whatever address that the processor is referring to. And this is the data address buffer from 87 to 80. And here is the control signal. So for example, the instruction is fetch, right? So we remember the three step. The first one is fetch, decode, and also execute. So let's say the first step, the instruction is being fetched, so it being stored inside the instruction register. And then another cycle, the instruction will be decode here. So from this register is being passed to instruction decoder here and machine cycle encoding, and then the instruction being decoded or being read here, and then after it being read, then it produce whatever the timing and the control signal that it has to send out. So this is the execution part. Okay. Yeah, these are all the function of control unit. Control microprocessor operations. ALU performs data processing function, and registers provide storage internal to CPU. Okay. All right, register. So register, remember class, register is memory inside the microprocessor. So we have here general, we call it as general purpose registers, which is we have a name for each register: B, C, D, E, H, and L, and each of these register B, C, D, E, H, and L is 8-bit registers. That means at one time it can store 8 bits of data. So this here B, we can store 8 bit of data. For example, 1 means that we have 4 bits of data, and we can use it singly, means that we can use to store data, mean each single location here, mean different data. For example, one data that is not related, we store it here B, and we store another data in C location. Or it can be used as 16-bit register pairs, or we can combine these two register to store one data. For example, we can combine the B and C register here. Instead of storing 8-bit of data, now we are storing the combined 16-bit of data, B and C, and then D and E, and also H and L. Okay, H and L can be, oops, okay, wait, guys. Okay, H and L can be used as a data pointer, holds memory address. Okay, we'll talk about this based on the instruction. H and L can be as a data pointer, which it store the memory address. So whatever instruction will be referring to the H and L register that store the memory address. And then we also have a special purpose register, which is the accumulator, and also yeah, which is the accumulator. So the accumulator is also storing 8-bit of data, and whatever operation that being done by the ALU will be stored inside the accumulator and store 8-bit data during IO transfer. And whatever IO transfer, mean, if we want to transfer the data from the if we want to transfer the data to the IO or from the IO, all of the data will be going to the accumulator. Alright, so flag register, and then the other thing is the flag register. Flag register is just the 8-bit register that show the status of the microprocessor before and after the operation. So whatever the operation occurred on the ALU, it will be reflected on this flag register. Flag register is just like a status register. For example, your phone, right? If there's a message coming in, then there will be a certain LED that will light up. For example, if the message goes into your WhatsApp, maybe the green light will comes out. It's just like that, so that it is telling the I mean, it wants to tell the status of the processing. Okay, so we have a different status here that can be represented by the flag register. For example, D7 is a sign flag. So if it's 0, it is a positive, and if it is 1, then it is negative. These are all something that you have to memorize, class. There's no other way of doing this. You have to memorize what is the specific function of each of these flag register. And also there is a 0 flag here, means that the 0 flags. Okay, what is this? Okay, wait. Okay, so the 0 flag here is if set, is set if result obtained after an operation is 0. For example, you do the operation and the operation is 0, then the 0 flag will be set to 1. And then the carry flag, if you are doing the arithmetic operation and you have a carry 1, then automatically the carry flag status will be 1. And then the auxiliary flag, if is set if there's a carry out of bit 3, and parity flag is set if parity is even and is cleared. So you can google what is parity class, and then parity flag is being uh, If the parity is even, then uh, the status here, the flag here, the parity P1 will be 1. If it's odd, it will be 0. Okay, and then the other thing, the register, we have the PC register, program counter register. You can see here program counter register. So the size of the program counter register is 16 bits wide. Because the purpose of program counter register is used to control the sequencing of execution of instructions. All of the instructions that you are fetching from the memory, this is the instruction. For example, you load your program, right? For example, you start from whatever move and load or whatever instruction. So step by step, all of the address that all of the memory address that's storing the specific instruction uh, will be stored inside your program counter. Means that the current instruction, for example, you are executing right now, move A instructions, right? So the program counter will store the address of the memory that store that instruction, the move instructions. Okay, that's why the register is used to control the sequencing. When you change, you fetch another instruction, then the program counter will be updated. It will be incremented to 1 to the another instructions, to your second instruction from the code that you wrote. And then this register always holds the address of next instruction, or sorry, so it holds the address of the next instruction. It is the same, so mean whatever comes next, I mean that is the instruction, that is the address that being stored inside the program counter. Since it holds an address, it must be 16 bits wide. Okay, remember class, the address bit size is 16 bits. The data size is 8 bit. You have to differentiate that. So if it address, it should be 16 bits. If it's data, it should be 8 bits. Okay, stack pointer. Stack pointer is also 16-bit register that is used to point into memory. If you remember in the when we cover about the memory, there is a stack pointer part where we assign the RAM, the random access memory, to be to act as the stack memory. So the stack memory is the temporary data that you want to store inside the RAM. For example, if you do the branch, or if you do the what they call the interrupt, so you want to store the current program counter, the address that you are currently processing, you want to store it somewhere. So the best place to store it is in the stack. So that's why you need to have the stack pointer too, because you need to point to which memory that you store the data. So that is your stack pointer. The memory this register points to is a special area called the stack. The stack is an area of memory used to hold data that will be retrieved soon. So the concept that they use for the stack is last in, first out. Whichever last that comes in will be the first that comes out. I mean, I've covered it in the previous lecture. If you haven't hear about this, you have to go through whatever lecture that I've already posted on the YouTube. Okay, non-programmable register. Instruction register is stored in IR after. Okay, this is the instructions that we cannot what do you call it, we cannot touch. I mean, this is the special non-programmable, means that it's being used by the microprocessor. The user cannot interrupt this. So this the purpose of instruction register is to store the instruction after it being fetched by the processor, and the decoder register decodes the instruction in the IR. Okay, this is the internal clock generator. So for example here, internally the clock is being generated is 3.125 megahertz, and the external clock is 6.25. This is the internal clock, built-in clock that being generated by the microprocessor, and this is the output clock. I mean, that means that this is the output clock that can be supplied by the microprocessor, 6.25 megahertz. Okay, the address and data bus. Okay, this is, yeah, this I've already covered. A8 and A15 is unidirectional because it is address bus, but the lower address, which is AD0 and AD7, is bidirectional, and it can be served as address bus A0, A7, and also data bus D0, D7. Okay, this is the multiplexing part where, okay, you can see this. We use the ALE signal to enable this latch, means that to enable to differentiate whether the bus is being used as address or data. To make sure we have the entire address for the full 3 clock cycle, we will use an external latch to save the value of AD0 and AD0 until AD7 until AD0 when it is carrying the address bits. We use the ALE signal to enable this latch. So normally, I mean, they'll put a latch here. Latch is just the transition. Okay, wait, show you the example. Okay, class, back to the latch. Okay, so we have to go through the explanation here. From the above description, it becomes obvious that the AD0 until AD7 until AD0 lines are serving a dual purpose, and they need to be demultiplexed, means that it can be function as a two functions. The first one is address and the second one is data. The high order bits of the address remain on the bus for 3 clock periods. So as you can see here, oops, that's the picture. Yeah, the high order bus. When this one has no issues because it will remain as the address bus for the 3 clock cycles. The issue is here because you have to switch it from the address and the to the data. So that's why they introduce the latch. So latch is kind of like, I mean, we can say like a temporary storage, to store the whatever value. Okay, so the high order bits of the address remain on the bus for 3 clock cycles. However, the low order bits remain for only a 1 clock period, and they would be lost if they are not saved externally. Yeah, so because, I mean, the low order of the AD0, AD7 until AD0 will only be remain for 1 clock cycle, and they will be lost if they are not saved externally. That's why they introduce the latch here. To make sure we have the entire address for the full 3 clock cycle, we will use an external latch to save the value of AD0 and AD0 until AD7 when it is carrying the address bits. We use the ALE signal to enable it. So as you can see here, I mean, they enable the ALE signal to store the AD0 and AD7 data here, and then after that it can be used as the data bus. I mean, that is the function of the latch. Given the ALE operates as a pulse during T1, we will be able to latch that. That means that latch is like you snap it. I mean, you snap the data and put it here, so it will be remain here until you change another address here. Then when ALE goes low, the address is safe, and the AD0 and AD7 can be used as the for the purpose of the bidirectional data lines. Yeah, this is how they do the multiplexing. This is the latch where they store the address, and all of the line here AD0 and AD7 can be used as the data bus. All right. Yeah, this is how it looks like in terms of the connections. This is your 8085, and this is your higher address bus being connected to this chip selection circuit, where you can have different memory devices, so you can choose which memory chip that it is the address is referring to. And then this is a lower 7 bit 8 bits of the address, it being stored in the latch when the ALE signal is set, and then it's point out to which location of the memory that you are referring to. And then when the ALE is after ALE already latched the address, it can be used as the data bus, where it can be used to send the data to the memory, or the memory can use it to send it to the microprocessor. and this is your control signal where you control whether where you tell the memory whether it is a read or write process. Okay, and then I'm gonna cover about this 8085 instructions. Okay, class. Actually, I think the most important thing that you have to master in this EKT 222 course is how to program the 8085. So you have to have the ability to write the program on your own. That's what I said. I mean, the project is really important on you. You don't write on the back of the people, so you have to do the coding on your own. You have to learn it. You have to try it. If you can write the program on your own. I'm sure that you can pass this course. So there might be a question in the exam that will ask you to. I mean, it's not mine. There will be a question in the exam that will ask you to do the coding. All right. Okay, so 8085 instructions. The instructions group can be grouped into five different groups. So if you look at the all of the 8085 instruction, you can category it. You can put it into five different groups. So there are instructions that being used for the data transfer operations, and also there are also instructions that are used for the arithmetic operation, addition, subtraction, whatever arithmetic operation, and then logic operations and XOR branch operations, asking the microprocessor to jump to another address to process another instruction inside of in the from the another address, and also machine control operations. Alright, so each instruction has two parts. The first part is the task or operation to be performed, which is the opcode, and then the second one is the operand. The second part of the data, we call it as operand. So this is the opcode. Example: move immediate, load, store, and this is the data transfer type of operations, mean which uh, involve the data transfer. Okay. This is the other thing that you have to know, that the data can be transferred between registers, and also the data, I mean, this is all the transfer mode. I mean, it can be transferred from register to register, and also it can be the data can be transferred from register to memory location, and also the data can also be transferred from memory location to the register, and also the data can also be transferred from the I/O device to the accumulator, or from the accumulator to the I/O device. That's why if you remember, when you want to set uh, what is the example that we used last time? Yeah, when we use the 8255, where we connect to this I/O controller, where we want to set which port as the input and which port as the output. We send the data to the accumulator first, and then from the accumulator we send it to the I/O device. Okay, the data in the source will not be changed. Okay, this is the example. You have to know all of this class, mean what is happening when these instructions being used. For example, LXI, for here LXIB will place the 16-bit number of 400 into the register pair of B and C. This is load immediate to the register where it will store whatever value. This is your opcode, and this is your operand here. Whatever the information that you need to execute based on the opcode. And then, for example, here you have to know, class, when you look at this operation, you have to know what is happening inside the memory. For example, here this 4000 is being loaded into the B and C register, because the LX normally it will store the into the register pair. For example, here B, the pair of the B register is B and C. and you have to know, for example, 40 goes here into the B register or goes into the C register. For in this case here, 40 goes into B register and 00 goes into the 0 C register. Okay, and then yeah, this one you have to go through it. I mean, this is really important class. You have to know each of the most important instruction. When I say most important instructions, that the instruction that you use the most in the lab, in your uh, projects, so that you have to know whatever happening when you execute the instructions. Okay, this one is using the other register. And then indirect addressing mode. So this is what they call indirect addressing mode. Okay, did they show the example? Okay, no. Okay, for example here, using data in memory directly without loading first into microprocessor is called indirect addressing. Indirect addressing uses the data in register pair as 16-bit address to identify the memory location being accessed. The HL register pair is always used in conjunction with the memory register M. For example, class, if there is an instruction opcode and then the operand is M, that means it refer to this HL register, where inside the HL register there is a 16-bit of address that identify or refer to the memory location. That is what we call indirect addressing mode, means that it use the address that's stored inside the HL register to refer to the specific memory location. Okay, and then this is the arithmetic operation, addition. I mean you have to know class what is the difference between this instruction add and also ADI, and also sub here, and with the SUI. You have to know what's the difference. You have to go through all the document and read it. And if you don't understand, you better go and ask your friend. Okay, what else? Yeah, this is the example of where you can use this indirect addressing mode at M. So actually it is adding the contents of the M to the accumulator. So whatever, I mean, the first thing, it will go into the HL register pair and take the address, and from the address it goes into the memory location and then get the data from the memory location and send it and add it to the accumulator. Okay, this is just the manipulating, and I mean these are all about instructions. You have to read about it. I mean, what is this instruction means and what is happen when you execute the instructions. Okay, logic operation. These are all the operations that you have to know. I think this is the most important thing about the instructions, and this is the what is the difference between this rotation. I mean RLC, RAL, RRC, RAR. I mean what are all the differences between each of the instruction? For example here, I mean how it being rotate. I mean what's the difference? You have to know all that, and you have to go through the documents, and we have it. If you don't find it, you have to Google it. And there's a branch operations, and there are two types of branch operations: the unconditional branch and also the conditional branch. So the unconditional branch is it will go to a new location no matter what, means that there's no condition for a branch. When you reach that instruction, that unconditional branch instruction, it will go to the new location. And this is conditional branch. Go to a new location if the condition is true. You put a condition there. If the condition is met, then you go to the new branch. Okay, this is the example of the unconditional branch. Whenever you reach this instruction, automatically it will go to the address being that you set here. Yeah, this is the conditional branch. You put the condition here. I mean it go to the specific address just if the zero flag is set. I mean this is all based on the flag. I mean this is the status register, right, which is updated from the ALU operation. Yeah, this is the machine control. I mean, for example, the HLT, which will tell the microprocessor to stop executing the program, means that done, stop, don't do anything. And this is no operation, exactly just do nothing. I mean, normally it is used for the delay purpose. Okay, this is the operand time. Okay, there are different ways for specifying the operand. So remember, class, uh, the operand is on the right side here. For example, this is your opcode and this is your operand. This is opcode, operand, opcode, operand. There may not be an operand. For example, here this instruction is not the operand is not needed for this kind of instruction, and this operand that can be consist of 8-bit number, so we call it as immediate data. So the operand can be immediate data here. For example, 4F is the immediate data, and also the operand can also be the internal register. So here B, you are referring to the B register, and also the operand can also be 16-bit address. Okay, depending on the operand type, the instruction may have different size. So the instruction have their own size based on how many operand that you have. Okay, so it will occupy a different number of memory bytes. Typically, all instructions occupy 1 byte only. Okay, normally all of the instructions only occupy 1 byte, means that only 8 bits. The exception is any instructions that contains immediate data and also memory address. Instruction that include immediate data use 2 bytes. So for example, if your instruction have immediate data, if you look into the memory, it will take 2 bytes to store this instruction and also the immediate data. If the instruction that include a memory address, normally it will occupy 3 bytes, means that 3 bytes, 8 times 3, 24 bits. One for the opcode and the other two is for the 16-bit of address. Here 2 byte because one for the opcode and the other one is for the 8-bit data. Okay, this is the operation instruction with immediate data. Okay, I think this is direct, and this is instruction with memory address JMP, and this is your go to the address here. 2085 is your this, because this is hexa, right? So this is 4-bit, 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 so it's 16 bits. And then okay, addressing mode. The microprocessor has different ways of specifying the data for the instructions. These are called addressing modes. So 8085, it has 4 addressing modes. The first one is implied CMA, which is doesn't have the I mean, it's a built-in and there's no address needed here. And then this is immediate, when you assign immediate value as the operand, and then this is direct, you assign direct address. And here is indirect because you ask it to load it, but the value is inside the register B. For example, here you assign the direct, you assign the value here, right? I mean, directly load into the accumulator this value, but this one is load the value from the register inside here, inside register B. Okay, data formats. Okay, I can jump. Alright, the counters and delays I won't cover about it. This is from your lab. So one of the things that you have to do before the test and or before the final exam, you have to go through all the labs. Make sure you understand the whole labs that you have done. I mean, what is the counters, how to do the counters, and you have to be able to write the code without looking at the notes, and how to perform the counter and whatever. Okay, let's skip this. And okay, a little bit of the timing diagram. Okay, I'm not sure, but I think just cover this thing because this is for me, I think it's important. For example, you have this instruction here, move immediate. and then the value here from 45 to the accumulator. Okay, and then okay, what will happen here? The first one is that here the ALE will be high. The ALE will be high here. Okay, class, come again. Okay, for example, uh, okay, for example here, this is a timing diagram for move immediate instruction. This is the immediate value and store it inside the A register. Okay, the first thing here is that it has to go to this address here, A000, to fetch the instructions move I. So what happened here in the first cycle here, the ALE signal will be set, so that the bus here is being set as the address bus. That's why you see here class A0, I mean this is the high order address bus which will not be affected by the ALE signal. The only be affected is just the lower order of the address bus. And then you can see when it's slash, then the data that represent here is the address. You see the address A000. This is the high order, this is the low 16-bit order, sorry, low 8-bit order. So that's why A000 H address here. That means it put the address so that it tells the memory that the processor want to refer to this address location. When it's low, now the bus here become the data bus. I mean this is the data that being sent by the memory, from the memory to the microprocessor 3E, because 3E represents the this opcode here, because opcode, if you change it in binary form MVI, you'll get 3E. I mean this move I signal in binary is 3E, because this is a machine code, the one that being understood by the microprocessor. So the value here from this memory location is being sent. So this is a memory location, so the memory will go into the specific location, take the value here and put it on the data bus, and then the data bus will send to the microprocessor. Okay, now that is the first step. So it involves here 3 cycles, not complete 4 cycles. And then the other cycles, what will happen is that the processor will ask to fetch the operand of the first instruction. So it will go to the next address, because the you remember right class, the one address location can only store 8 bit of data. So if you have opcode and also one operand, you have to use two location, 2 bytes. So here the operand is being stored inside another address location, which is just next to this address. And that's why you can see the next address is A001. That's why here when the ALE is high, the bus here, the lower order bus is 01, which refer to the address location that the memory has to go to fetch the value. And then after it fetch the 45 value, and it put it on the data bus here 45, and send it to the microprocessor. That is basically the timing diagram, and it's almost the same for all of the operation, how the microprocessor fetch the instruction, and also so instructions, which means the opcode and also the operand. All right, okay, this one you can go through it class, because you can see here this is the opcode fetch cycle. You can see what happened here, and you refer to the value, and then you can see here memory cycles. This is memory read cycle, and also memory, this is also memory read cycle. Okay, what else is important? Okay, just jump this thing. Okay, memory, I won't cover it because I just covered it in the previous lecture. You have to go and watch it online. Okay, what I want to say about memory is mainly about theory. So you have to really do the reading, and you have to memorize most of the parts. Okay, interrupts is also the same, but for interrupt class, I think you can also refer to the I've already made online lecture on the interrupt. So for interrupt, the most important thing is that the first thing you know the type of interrupt, and then the second thing is the interrupt process, what happened when the interrupt pin is high. So step by step, you have to know what is happening, how the processor react to the interrupt, and then the last one is how to write the code to trigger or to service the interrupt. All right, I think that's all class. So I wish you guys all the best for your exam. So see you tomorrow.